Hello guys, welcome to this video series on linear algebra for engineers. In our last video, we defined rank of a matrix A as dimension of column space of A, where A was an m by n matrix. In today's video, we're going to prove a very important result, which says that dimension of column space of A equals to dimension of row space of A. Okay, so before we do that, first let's define two different types of ranks. So here A is an m by n matrix, and we're defining column rank of A as dimension of column space of A, and row rank of A as dimension of row space of A. And in this video, we're going to prove this result, which says that dimension of column space of A equals to the dimension of row space of A. In other words, column rank of A equals to the row rank of A. Okay. So if this result is true, dimension of column space of A is same as the dimension of row space of A, then we could have defined rank of A as dimension of row space of A. Okay, that will be equally good. Okay, so let's prove that. So let R be the row rank of A and C be the column rank of A. Okay, row rank of A is R, meaning dimension of row space of A is R. That means there exists rows, say B1, B2, BR of A, which form a basis of row space of A, right? Point is there are many basis vectors because dimension is R. Okay. This means that every row of A is a linear combination of these BIs, right? Okay, so I'll denote ith row of A by this notation, I dot, and I will denote, so this will mean ith row of A, and ith column will be denoted by this thing. Okay, now since every row of A is a linear combination of BIs, EI dot equals to some linear combination of BIs, right? That means there exist constants,Cijs, such that Ci1 B1 plus Ci2 B2 plus dot 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 CIR BR. And how many rows are here? A is an m by n matrix, so m rows and columns. So I ranges from 1 to m. Okay. Now we can write A as A1 dot first row, second row, the mth row. All right. And this can be written as by matrix multiplication B1, B2, BR, and here we have these coefficients. So first we'll have C11, C12, C1R dot CI1, CI2, CIR. Finally, we have CM1, CM2 dot 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 CMR. So what is the order of this C matrix? So there are M rows and R columns. So this should be M by R. And what is the order of this B matrix? Well, note that each BI is a row of A, and row of A is 1 by n because A is m by n. So in this matrix, there are n columns and r rows. So it is r by n. Right? Let's denote this bi matrix by B and this di matrix by C. So we have A equals to CB. Okay. Now note that we can write it like this. So C and columns of B are dot one, following our earlier notation. Second column, and there are n columns, and this can be written as C B dot one, C B dot two, dot dot C B dot n. And what are these? So this matrix equals to A. So this is basically the first column of A, right? So we have ith column of A equal to CB dot I, and I ranges from where to where? How many columns are there in A? There are n columns in A. So I ranges from 1 to n. So this b dot I is a column vector and it is being multiplied with c. So we have a linear combination of columns of c, right? So this is a linear combination columns of c, right? So every column of A is a linear combination of columns of C, right? This means that column space of A is a subspace of column space of C, which means the dimension of column space of A has to be less or equal to dimension of column space of C. We denote this quantity by C. We set this notation earlier here. C is the column rank of A, that is dimension of column space of A. So C is less or equal to dimension of column space of C. Okay. Now, how many columns are there in C? So C has M rows, R columns. So there are R columns in C, right? That means column space of C is spanned by R vectors, right? The R columns, and therefore its dimension, or should I say, the number of linearly independent vectors, or should I say, to be more precise, set of linearly independent vectors in this cannot be more than R. Its dimension is to be less or equal to R. So C is less or equal to R. In other words, we have proven that for every matrix A, dimension of column space of A is less or equal to the dimension of row space of A, right? So since this is true for every matrix A, this is in particular true for A transpose, right? Let's denote this relation by star. So star is true for A transpose. Therefore, we have dimension of column space of A transpose less or equal to dimension of row space of A transpose. But column space of A transpose is row space of A. So we have dimension of row space of A. These are equal, right? Because columns of A transpose are rows of A by definition of transpose. So dimension of row space of A is less or equal to dimension of column space of A. But this means that R is less or equal to C, right? And here we had C less or equal to R, and here we have R less or equal to C. So by 1 and 2, R equals to C. This proves the theorem. Row rank equals to column rank. And what is one immediate consequence of that? Immediate consequence is that, well, in the last video, we defined rank of A to be dimension of column space of A, right? Now we can define it as this as well because they are just the same thing. Row space of A. And another consequence is, well, what is rank of A transpose? Rank of A transpose is, as per a definition, dimension of column space of A transpose, right? And columns of A transpose are rows of A. So this is equal to dimension of row space of A, and dimension of row space of A is equal to dimension of column space of A. That means this is equal to the rank of A. So A and A transpose have the same rank, right? Now, what can we say about rank of A plus B? Can we say that rank of A plus B equals to rank of A plus rank of B? Can we say that? No, because if we take A equal to the identity matrix and yn, say 2 by 2 identity matrix, and B equal to negative of 2 by 2 matrix, then A plus B, rank of A plus B equals to, what is A plus B? It is 0, right? So rank of 0 matrix, 0 matrix, right? 2 by 2 0 matrix, oxygen. Okay, so this is equal to dimension of column space of 0 matrix, and column space of 0 matrix is what? Is 0 space. And what is dimension of 0 space? 0. So rank of A plus B is 0. But rank of A equals to dimension of column space of A is column space of identity, which is 2 in this case. So 2. This is same as rank of B. So this is clearly not equals to 2 plus 2. So the answer is, it doesn't have to be true, right? So no, it is not true. Okay, so thanks for watching this video. I'll see you in the next video. Bye bye. Take care.